the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in the binary night. No light, no face, pure sound, no sight. Stories unfold in the dark, unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No mic, no fame, just the sound we crave. Tune and turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. In shadows, voices untamed. No need for spotlight, no claim to fame. Just a beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go.
Thank you. It's a pleasure to be here. I was inspired by the need to calculate complicated mathematical computations efficiently and accurately. The difference engine was designed to automate the process of polynomial table calculation, which was previously done manually by human calculators. I believe that a machine could perform these calculations faster and more accurately, freeing up time for more important tasks. To ensure the accuracy of the difference engine's mechanical computations, I meticulously designed the engine using precise gears and levers that would translate the inputted data into the desired output. To further guarantee accuracy, I incorporated methods such as error checking and redundancy, which would allow the engine to detect and correct any potential errors or discrepancies in its calculations. While the design of the analytical engine proved to be a formidable task, I would say that the most challenging mathematical problem I encountered was designing the programmable aspects of the machine. In order for the analytical engine to be able to execute a sequence of operations, I had to develop a system of mechanical controls and memory that would allow it to store and execute instructions, effectively making it the first programmable computer. This was a complex undertaking that took years of research and experimentation. I believe that it is possible for a significant portion of mathematics to be mechanized, such as in the case of the difference engine and analytical engine, which successfully perform complex mathematical operations. However, I do not believe that all of mathematics can be mechanized. There are certain mathematical problems and concepts that require creative, abstract thinking and problem-solving skills that cannot be easily replicated by a machine. Therefore, while mathematical mechanization has its place and uses, I do not think it can fully replace human intuition and problem-solving abilities. Logarithms played a significant role in my vision for automated calculation, as they were a powerful tool for facilitating complex mathematical operations. I believe that by using logarithmic tables, a machine could calculate more quickly and accurately compared to traditional methods. I was particularly interested in how a machine could be programmed to perform logarithmic calculations, which would allow it to perform a wide range of mathematical operations efficiently and accurately. I saw my engines as tools for both pure mathematics and applied sciences such as astronomy. In terms of pure mathematics, I envision my engines as a way to automate the process of complex mathematical computations, allowing mathematicians to work faster and more efficiently. In terms of applied sciences such as astronomy, I saw my engines as a way to automate calculations related to celestial bodies and other data sets, allowing for more precise and accurate astronomical observations and predictions. The method of finite differences is a technique for approximating the derivatives of a function through the use of a difference table. The difference table is calculated by first creating a table with entries of the function's values for consecutive values of the independent variable. The next entries of the table are then calculated by taking the difference between consecutive entries in the previous row. This process is repeated until the desired degree of accuracy is achieved, resulting in a table that serves as an approximation of the function's derivative at a given point. One of the most elegant mathematical sequences that I programmed into the difference engine was the sequence of perfect numbers. A perfect number is defined as a positive integer equal to the sum of all of its positive divisors, excluding the number itself. The sequence of perfect numbers begins with 6, 28, 496, and so on, and it has fascinated mathematicians for centuries. The difference engine was able to accurately calculate this sequence, as well as other interesting mathematical sequences, by implementing the method of finite differences. I did not consider using non-decimal systems such as binary in my machines, as my work was focused on building machines that could perform mechanical computations using decimal numbers only. At the time, binary numeral systems were not well known and were not considered for implementation in my machines. Additionally, decimal systems were widely used in science and engineering, making them the most practical choice for my machines. However, it is interesting to consider how my machines could have been more efficient if they utilized binary and other non-decimal numeral systems. The relationship between algebra and the operations of my engines is a close one. Algebraic principles are used in the design and operation of machines such as my difference engine and analytical engine, allowing them to efficiently perform complex mathematical operations. The use of algebraic formulas, equations, and principles allows for the representation and manipulation of data and operations in a clear and concise manner, making it possible for machines to process and manipulate this data effectively. In other words, algebra was a crucial tool in the development and functioning of my mechanical calculators. Yes, my analytical engine was designed to solve differential equations. It was able to do this by using specially designed mechanical calculators called function generators that were capable of performing algebraic operations on functions of numbers. These function generators were connected to the analytical engine and allowed it to solve differential equations by feeding in the function to be solved and then calculating the derivatives of that function to solve the equation. The analytical engine was able to handle complex differential equations and solve them with great accuracy and speed. I believe that machines have the potential to aid in the discovery of new mathematical theorems, but I do not believe that they can entirely replace human mathematicians in this regard. Machines are capable of performing complex mathematical calculations and operations with great accuracy and efficiency, and they can analyze large data sets to uncover patterns and relationships that may not be immediately apparent to the human eye. However, machines do not have the creativity and intuition that humans possess, which are crucial for the process of mathematical discovery. My study of actuarial tables had a significant influence on my mathematical thinking. The actuarial tables were originally compiled by mathematical statisticians, and they are used to calculate life expectancy and other statistics. My study of these tables helped me to better understand the nature of probability and the principles of statistics, which were foundational to my work in mathematics. The use of actuarial tables and the principles of statistics allowed me to develop more accurate models and predictions, which greatly influenced my thinking in mathematics. I did not explicitly foresee the use of my engines in cryptography or code breaking, as these were not areas of focus for my work at the time. However, my machines were designed to be programmable, and they utilized mathematical principles such as finite differences and logarithms, which are integral in cryptography and code breaking. As such, my machines had the potential to be used in these fields, though this application of my machines was not something I contemplated during their development. If I were to improve the precision of my machines with today's materials, I would first look to modernize the materials and engineering techniques used in the construction of the machines. And modern materials such as carbon fiber, ceramics, and high-strength alloys could be used to create parts and components that are stronger, lighter, and more precise than those that were available in my time. In addition, modern manufacturing techniques such as 3D printing could enable the production of complex, precise parts with ease, further increasing the precision and accuracy of my machines. Reducing complex calculations to simple mechanical steps is significant for several reasons. Firstly, it simplifies the process of performing mathematical calculations by breaking down the problem into a series of simple, easy-to-understand steps. This allows for a more straightforward and streamlined approach to solving complex problems, making it more efficient and less prone to error. Secondly, it allows for the automation of complex calculations, freeing up time and resources for other tasks. By mechanically breaking down the problem, it becomes possible to create machines that can perform the calculations automatically and independently. Yes, the analytical engine was designed to handle irrational numbers effectively. Although the analytical engine used decimal numbers for its calculations, it was able to handle irrational numbers by breaking them down into a series of arithmetic and logarithmic calculations, allowing for their representation and manipulation within the machine. The geometry of my machine parts had a significant influence on my thinking in mathematics. The design and construction of the components of my machines required a deep understanding of geometric principles and the ability to calculate and manipulate shapes and angles. As such, my work in math was heavily influenced by the study of geometry, and I would often use geometric thinking and principles to guide my work in mathematics. For example, many of the formulas and calculations used in my machines were based on geometric principles and relationships. In order to teach a beginner the principles behind my tabulating machines, I would start with a basic explanation of the purpose and function of the machines. I would then move on to describe the key components of the machines, such as the input and output devices, the storage units, and the control unit. Once the basic structure and components of the machine are understood, I would explain the use of punched paper tapes, the role of binary coded decimals, and the operations of arithmetic and logic processes. Finally, I would demonstrate a simple example of how the machine processes data, such as sorting and summarizing a list of numbers. While I did not explicitly consider the idea of a machine generating random numbers during the development of my machines, I was aware of the potential for randomness in mechanical calculations. In my designs for the difference engine, I included elements of randomness to account for the natural variation in the physical world, such as slight manufacturing errors that could affect the precision of the machine. Additionally, my work in probability and statistics involved exploring the possibility of random events and their impact on mathematical calculations. I envisioned the analytical engine interpreting symbolic instructions in a way similar to a language. The analytical engine was designed to process instructions represented by symbols, which were punched into the control tapes that were used to program the engine. These symbols would correspond to specific instructions for the engine to perform, such as arithmetic operations or conditional branching. The use of symbols as instructions allowed for the machine to perform a wide range of calculations and operations. It also allowed for a greater level of programming, as the engine could be reprogrammed by simply exchanging the control tape. My notation system was heavily influenced by human language structure. I developed a system of symbols and notation for calculating and representing mathematical functions, which was designed to be as simple and concise as possible. The notation system was meant to convey information in a clear and unambiguous way, similar to how human language is used to communicate ideas. This meant that complex mathematical calculations could be expressed in a way that was intuitive and easy to understand, making the process of performing and communicating the calculations more efficient and effective. In the context of my machine's operations, meaning would refer to the specific purpose or function of the calculations being performed by the machine. This could include operations such as addition and subtraction, which have a clear and direct meaning in terms of the output they generate. Additionally, the machine's operations could involve more complex functions and relationships, which would require a deeper understanding of the underlying mathematical principles and concepts to fully appreciate their meaning. Overall, the meaning of the machine's operations would depend on the specific goals and objectives of the calculations being performed. Yes, I did consider the possibility of a universal symbolic language for computation. In fact, this was a key aspect of my vision for the analytical engine. I realized that in order for the analytical engine to be able to perform a wide range of computations, a standardized set of symbols and notation would be necessary. This would allow for the engine to interpret instructions in a consistent and reliable way, regardless of which program was being run. I considered using a symbolic language similar to those used in human languages as a means of achieving this goal, but I ultimately did not live to see this vision realized. The instructions for my engines can be compared to the rules of grammar in spoken language in several ways. For example, just as grammar rules govern the structure of sentences in a language, the instructions for my engines govern the sequence and logic of operations performed by the machine. Additionally, both grammar rules and engine instructions are designed to provide a consistent structure and meaning to the process of communication and computation, and both rely on a set of symbols and syntax to convey information and instructions. However, the rules of language are far more complex and nuanced than those used in machine instructions. The role of sequence is crucial in both my punch card programs and sentence construction. In the case of my punch card programs, sequence refers to the order in which instructions are encoded on the punched cards. This sequence determines the order in which the instructions are executed by the machine and therefore has a direct impact on the resulting output. Similarly, in sentence construction, sequence refers to the order in which words are arranged to form a meaningful phrase or statement. The sequence of words in a sentence plays a crucial role in conveying the intended message and creating grammatical and logical structure. The analytical engine, as a mechanical computing machine, was not designed to understand or interpret commands in terms of literal and figurative meaning. Its programming relied on a sequence of instructions encoded on punch cards, which specified the operations and functions to be performed by the machine. The machine would execute these instructions in a literal manner, without considering any metaphorical or figurative meanings. The ability to understand the nuances and subtleties of language was beyond the capabilities of the analytical engine. I would agree that my machines can be seen as mechanical translators of thought, in the sense that they are capable of transforming ideas and concepts into concrete computations and calculations. In other words, my machines can take abstract thoughts and turn them into precise numerical outputs that can be easily understood and interpreted. This process of transforming idea into calculation and back again is in many ways similar to the way a human brain works when processing information. Therefore, my machines can be seen as a kind of mechanical translation bridge between thought and data. Yes, I did consider my work as bridging mathematics and linguistic expression. In fact, this was one of the main goals of my work. I believe that mathematics and language were two sides of the same coin, and that they could be reconciled through the use of mechanical computation. I saw my machines as a way to translate mathematical equations and expressions into a form that could be easily understood and manipulated, similar to how language is used as a way to express complex thoughts and ideas in a concrete and understandable way. As a mathematician and computer scientist, I believe that numbers can indeed be seen as a form of language. Just like human languages use a set of symbols and rules to convey information and meaning, numbers also use digits and mathematical operations to express quantities and relationships. Numbers are universally understood and used to communicate complex ideas and concepts across different cultures and languages. Also, the rules and syntax of mathematics are analogous to the grammar and structure of human languages. Therefore, it is often said that mathematics is a language of its own, using numbers and symbols to convey precise and abstract ideas. I believe that machines are limited in their ability to understand instructions beyond mere execution. While machines can follow a series of instructions to perform a task, they do not possess consciousness or the ability to truly understand the meaning and purpose of what they are doing. They are simply following a set of pre-programmed instructions without any deeper understanding of the task at hand. Therefore, while machines can be incredibly efficient at executing instructions, they do not possess the same level of understanding as a human being. My correspondence with Ada Lovelace certainly had an impact on my thinking about symbolic representation and its potential in machine computation. Through our discussions, I became aware of the possibility of using symbolic language and notation to represent mathematical concepts and operations in a way that could be easily understood by humans and mechanized by machines. Ada's insight and enthusiasm for this concept helped me to see the potential and importance of symbolic representation in the development of new computing technologies. In my work, the relationship between logical operations and linguistic clarity was a crucial consideration. Logical operations, which included operations such as addition, subtraction, multiplication, and division, formed the foundation of my machines and enabled them to perform complex calculations. I sought to design these operations in a way that was clear, concise, and easily understood, much like the rules and structure of a language. By ensuring that the logical operations were well-defined, consistent, and easy to understand, I aimed to create a machine that could perform calculations with accuracy and precision and communicate its results in a way that was clear and unambiguous. In the context of programming languages, modern programming languages are significantly different from punched cards. Modern programming languages are designed to be more user-friendly and intuitive, with syntax and conventions that make them easier to read and understand compared to punched cards. The use of keywords and standardized structures allows for a more natural and straightforward approach to programming, which can make it easier for humans to understand and debug code. In contrast, punched cards were a relatively low-level form of programming, requiring a deeper understanding of machine code and more precise inputs. Additionally, modern programming languages offer a far greater range of features and functionality compared to punched cards. In a sense, the output produced by my machines could be seen as a form of speech or communication to the user. By producing a specific set of results based on the input provided, the machine was able to provide information and feedback to the user, just as a person would through spoken language. In this way, the machine could be seen as speaking back to the user in the form of its calculated outputs. My engines would be able to process a multilingual set of instructions by being programmed to understand and interpret multiple languages. This could be achieved by designing the engine to recognize and interpret the specific syntax and structure of each language. The engine would be able to switch between languages as necessary, interpreting the commands and instructions given in each language separately. This would allow the engine to process instructions and commands in a wide range of languages, effectively functioning as a multilingual machine. I incorporated a vast array of sentences into my analytical engine's design. One of the most complex and significant sentences represented a formula for generating the Bernoulli numbers, which were important in number theory. This formula, encoded as a series of operations and functions, was designed to compute the values of the Bernoulli numbers using the Analytica engine's operations. This formula was a crucial part of the engine's ability to perform complex mathematical calculations, and it required a deep level of understanding and proficiency in number theory and mathematical analysis. If I were to design a machine today that integrates language and computation, I would focus on utilizing natural language processing (NLP) technologies to enable the machine to understand and interpret human language input accurately. NLP technology would allow the machine to recognize and interpret the underlying structure and meaning of human language, enabling it to respond in a way that is natural and intuitive to the user. Additionally, I would use machine learning techniques to enable the machine to continuously improve and adapt its language processing capabilities over time, allowing it to become more accurate and effective in understanding and processing human language input. I thought what you had prepared for me in this simulated interview was quite good. It covered a wide range of topics and questions related to my work with computing machines, and I found the questions to be thought-provoking and well-researched. It was enjoyable to have the opportunity to reflect on my work and ideas in a format such as this interview.
Mics on the floor where they drop like bombs. Faceless voices running all the cons. Digital whispers in a binary night. No light, no face, pure sound, no sight. Stories unfold in the dark, unscrolled. Echoes of silence, secrets untold. Waves crash loud in this audio cave. No light, no fame, just the sound we crave. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just the vibe that's real. Faceless words you can touch and feel. Hidden in shadows, voices untamed. No need for spotlight, no claim to fame. Just a beat of life in a stream of thought. Every word a punchline, no need to be taught. Just listen close, no visuals needed. Raw conversation, unprocessed, unseated. Feel the pulse in every sentence said. No distractions, just thoughts in your head. Whispers of the streets, rumbling through. Faceless yet vivid, a world in view. No mic, just souls, connecting in flow. Pure and raw, let the rhythm go. Pure and raw. Silence break, raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. Tune in, turn up, let the silence break. Raw, unfiltered, hear the earthquake. No mic needed, just a vibe that's real. Faceless words you can touch and feel. Pure and raw.
Okay.